types of heads in turbines. Okay, so in turbines we talk about two types of heads. One is the gross head, and second one is the net head. Now this gross head is the difference between the head race level and the tail race level. Okay, so this difference of head race level and tail race level, this height we call as gross head. Now the another name for this head is the total head. Okay, then the net head is the head available at, this is the head available at the turbine inlet. Okay, so you can say this is less than that of the gross head by an amount equal to some friction losses in the flow passage, okay, or the height from the tail race to the turbine inlet. So these two parts you have to reduce from the gross head, and the resulting part you have is the net head. Okay, so from gross head you can say you have to reduce the frictional part, okay, plus the height of tail race level and the turbine inlet. So that is the net head. Now the other names for net head are one is effective head. The another name is effective head. Okay, this is also called the available head. Okay. Now if you see the diagram of hydropower plant over here. Okay. So this height, this yellow height, this is the total or gross head. Okay. And this height, okay, this is your net head, your working head, your available head, or effective head. Okay, so this is the difference between the two types of heads in the turbine. So now we take the different types of losses. So different losses in turbines. The first loss is the head loss in penstock. Now this is the friction loss in the pipe of penstock. So this value you can got from Darcy-Weisbach equation. Okay, so that is used for determining the frictional loss in the pipe. So the first loss is head loss in penstock. The second is head loss in nozzle. Okay, so nozzles are there only in impulse turbine. So this loss is only in the impulse turbine, and again this loss is due to nozzle friction. Okay, this loss is due to nozzle friction. Third loss is hydraulic losses. Okay, so these losses, so different in different turbines. In impulse turbine, so you can say in impulse turbine, the hydraulic losses occurs due to blade friction. Okay, due to eddy formation and the kinetic energy of the leaving water. Okay, so this is the kinetic energy of water that is going to the tail race in the form of some energy. So that water which after striking to the turbine goes into the tail race have some velocity. So corresponding to that velocity, we have the kinetic energy, and that energy is one type of loss in the turbine. So that contributes in the hydraulic loss of the impulse turbine. Okay. Now in case of reaction turbines, apart from all these losses, there is one more loss that is due to friction in the draft tube. So in reaction turbine, we have one more component that is called draft tube. Now this draft tube connects the outlet of the turbine to the tail race. So again, this is one type of a pipe of enlarging cross section. So the friction in that contributes as the hydraulic loss in reaction turbine. So draft tubes are present only in reaction turbines. Then another loss is the leakage loss. Okay, so you can say in case of impulse turbines, whole of the water may not be striking the buckets. On the runner, in case of impulse turbine, we have the blades, or we can call them as buckets. So whatever water coming out from the nozzle, the whole amount does not strike on the buckets. So some of the water may go waste as this is not striking on the bucket. Okay, so that part we consider as the leakage loss. Okay, so you can say in case of impulse turbines, whole of the water available does not strike on the bucket. Okay, now in case of reaction turbines, Some of the water may be passing through the clearance between the casing and the runner. There is some gap between the casing and the runner, that is the clearance. So some water may go waste, or you can say directly goes to the tail race through draft tube, okay? Not striking on the runner. Okay, so that amount we consider as the leakage loss. Okay, that is comes under the leakage loss. Another type of loss we have the mechanical loss. Okay, so the power produced by the runner is not available as the useful work of the shaft. This is because of some power may be lost in the bearing friction as mechanical loss. So whatever the power produced by the runner, that total power we cannot convert into the useful work, useful shaft work. Okay, so there is some loss of that produced power, that is in the form of bearing friction. Okay, so this bearing friction contributes the mechanical loss. Then one more type of loss is the generator loss. So due to this loss, the power produced by the generator. So ultimately you have to produce the electricity from the generator or alternator. So the power produced by the generator is still lesser than the power obtained at the shaft output. Okay. So the power produced by the generator is less than the power available at the shaft. So again, that difference is due to this generator loss. So that may be in the form of some winding in the generator, okay, that is in the form of some humming. So something like that, the losses which are occur in the generator comes under the category of generator loss. Okay, so these are the various losses in the turbines. Now, if we want to account all these losses, so accordingly, we have the different efficiencies in the turbines. So to account all these losses in the turbines, we have different efficiencies. The first efficiency is the hydraulic efficiency. Okay, so it is noted by eta H, and it is defined as the ratio of the power developed by the runner to the actual power supplied by the water to the runner. You can say eta H is the runner output divided by the actual power supplied to the runner. This is hydraulic efficiency. Okay. Now this efficiency accounts the hydraulic losses. Now, if you want to see what is the actual power supplied to the runner, now uh, we have say total Q. Now Q is the amount of discharge coming from, or you can say coming through the penstock. Okay. So say out of this Q, small q is the leakage loss, or you can say this much amount of water striking the runner. So q minus q is the amount of water that is striking the runner. So power corresponding to this discharge. So this is the discharge. Say H is the net head. Okay. So actual power supplied, now you can say this is equal to runner output divided by WQ minus Q into H. So small q is the leakage loss. Okay, so this is the actual power supplied to the runner. So runner output divided by this term gives us the hydraulic efficiency. Now, if we talk about the term WQH, now this WQH is power available. This is the power available, and this term you can say the power supplied to the runner. That is with respect to Q minus Q. Okay. Now to account the volumetric losses, we have another efficiency that we call as volumetric efficiency. This is eta V. So it is the ratio of the actual quantity of water striking the runner to the quantity supplied to the turbine. So you can write eta V as uh, Q minus Q divided by capital Q. That is volumetric efficiency. Third efficiency is the mechanical efficiency, denoted by eta m. So this efficiency accounts the mechanical losses, and it is the ratio of the shaft output to the runner output. Okay, so eta m you can write as shaft output divided by runner output. Okay, so there is one more efficiency that we call as overall efficiency. That is eta O. Okay, so this is the ratio of shaft output to the power available. Okay, at the turbine inlet. So you can write eta O as shaft output divided by power available at inlet. Okay, so this power available at inlet, this I can write as WQH. This is overall efficiency. Now I can also write this overall efficiency as equal to shaft output divided by runner output into runner output divided by W Q minus Q into H into Q minus Q divided by Q. So ultimately I have shaft output divided by WQH. So you can see runner output cancels with this runner output and Q minus Q cancel with this. So shaft output divided by WQH, that is overall efficiency. Now you can see over here now, this is equal to, now shaft output to runner output, that I can write as mechanical efficiency. Runner output to W Q minus Q into H, that is my hydraulic efficiency. Okay, and the last term Q minus Q by Q is volumetric efficiency. Okay, so now I can say the overall efficiency is the product of other three types of efficiencies, eta M into eta H into eta B. Okay, so this is all about the efficiencies we have. Okay, so thank you.